when I did my partial fraction decomposition, first of all, I ended up with 1 over n plus 2 minus 1 over n plus 3. So then when I wrote out the first 4 terms, notice my 1/4 will go away, my 1/5 will go away, my 1/6 will go away, and I know eventually my 1/7. So what's the only term that's going to remain? 1/3. So it is going to converge to 1/3 by your telescopic sum. All right. So now let's take a look at D. 3 over k plus 1 to the second minus 3 over k to the second. So obviously when I see these two fractions subtracted, again, when I'm checking for convergence and what it's converging to, geometric or telescopic, because I've already got my two fractions that are subtracted, this is where, what do you think you're going to check for first? Telescopic. So you guys go ahead and check to see whether or not this will converge by your telescopic and what it will converge to. Again, don't reduce your fractions. This is where, guys, you don't always assume when you're dealing with telescopic, you're just going to be, it's always going to be the first term. That's why you want to write out at least about 4 terms to clearly see what the pattern is. So this is what the first 4 terms look like when I wrote it out. So does the 3/4 go away? Yep. What about that 3 minus 3 over 1? No. The 3/9 goes away, the 3/16 will go away, and eventually another 3 over 25. So what is this going to converge to by your telescopic sum? This is going to converge to what? Converges to -3. So any questions, guys, on how you can check the convergence of a telescopic or geometric? Like I said, in the directions and on the AP exam, when any time they're asking you to find, again, we're only talking about the infinite series. Anytime it's an infinite series and they're asking about what it's converging to, only 2 series that you can find what it's converging to is the geometric or the telescopic. All right? Yes, Brian?
The first one is the denominator of the coordinate factor like the now start the third term, which means the third term of the 1 over n. We have a variable between 1 and add 1. So 1 over n plus 2 is the third term. That means all the terms after that would be matched to 0. So that means only the first term would be the one that's remaining. So we need to add the first term to 1. And then same thing for b. So a minus k plus 1. The only difference between that, k plus 1 and k, would be 1 term. So only the first term would remain. So that's why it was 1. And then for c, 1 over n plus 2 minus 1 over n plus 3. The only difference is also just the first term. That's the last one. 3 over k plus 1 minus 3 is 3.
And you better be real short. You better be real short about your logic. Any questions on that? Yeah. Look at that, write it down. That's short, write it down. Okay.
So if you write it out, it's
Mhm.
if you write it out or we're
Yes. All right. So another popular series is the harmonic. The harmonic series is probably one of the most important ones we're going to study, one of the most important of all diverging series. And actually, you musicians, when you get to your project at the end of the year, if you want to, you can do a lot with the harmonic series. Because there's a lot to do with a vibrating musical string and overtones. So we'll talk about our project at the end of the year, but that you could, those of you that are very interested in music could probably come up with a good project on the harmonic series. The harmonic series. Again, guys, we're dealing with your infinite series. It's your special series that you're looking at 1 over k. So again, obviously, if you write out your first few terms, you have 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. So if you just look at the list of numbers, you can see that the sequence is converging to 0. But it is not obvious that the series also, converges or diverges. So this is the trick with the harmonic series. The harmonic sequence will converge. However, the harmonic series diverges. So again, although the divergence is slow, by using partial sums, the divergence would become apparent. So what you need to remember about your harmonic. The harmonic sequence converges to 0. However, the harmonic series diverges. What's happening is when you look at the graph of 1 over x, again, we're starting with 1 over k. Again, 1 over k, the graph looks something like this. So again, when you're looking at adding all these terms together, you're actually finding the area under the curve. It's not coming down fast enough. In other words, it's not getting closer and closer to 0 quick enough to say that the series is going to converge. When we study the p-series, we're going to get a little bit more into depth in that. We talk about the p-series. The sum of the harmonic sequence is a subset of the values of the function 1 over x. So, let me show you the convergence of the harmonic sequence. Again, when you take a look at 1 over k from k equals 1 to infinity again, we're looking at k is equal to 1 to infinity. So early in the chapter, you talked about how you can find about whether or not a sequence converges or diverges. So I'm going to find the limit as k approaches infinity of 1 over k. And what is the limit as k approaches infinity of 1 over k equal to? This is equal to what? 0. So therefore, what does that tell us about the sequence? The sequence is going to converge. Again, we're talking about the sequence, remember, versus series. So now let's talk about showing why the harmonic series diverges. So remember, when we're adding all the area under the curve, this k equals 1 to infinity of 1 over k, we can rewrite this as an integral. From k is equal to 1, k is equal to 1 to infinity up to x, with x equals 1 to infinity of 1 over x dx. So this goes back to your favorite chapter 7, using the improper integral. When you have an upper bound that's infinity, what are we going to do with this integral? We're going to rewrite it as what? The limit as b approaches infinity from x equals 1, I don't have to bring x equals 1 to b. From 1 to b. Of 1 over x dx. The antiderivative of 1 over x is going to be what? The limit as b goes to infinity of 1 to b. So I know the antiderivative of 1 over x is going to be the natural log of x. And again, I have to evaluate this from 1 to b. So the limit as b approaches infinity of the natural log of absolute value of b minus the natural log of 1. The natural log of 1 is just going to go away. This is going to 0. So now the big question is, what is the limit as b approaches infinity of the natural log of b? So this is where you need to kind of remember the end behavior of your natural log function as you're approaching infinity. Remember, we have a vertical asymptote that's going towards what? Infinity. So now remember what's going to happen with this integral then. If the limit is going to infinity, is this integral going to diverge or is it going to converge? Diverge, so divergence. Yeah, the harmonic series is just the 1 over k. What you have to remember is the sequence converges, but the series is going to diverge. We'll talk, it's part of the P series, but we'll talk about the P series next class, or the class after that. If I change this to 1 over x squared, it's a completely different animal. If I change that to 1 over x squared, we're dealing with a completely different situation, and that's a P series. And we'll talk about, and the harmonic series is a part of a bigger series called the P series, but it's a very special case of the P series. Yes? You'll learn to love the P series when you're doing convergence and divergence, trust me. Yes, Jonathan? Well, that would be your alternating series, and that's a whole other animal. We'll study the alternating series later too. All right, guys.